Welcome to Lecture 3.2, Parity and Proving Existential Statements. We'll start with a few definitions of things you certainly already know, but the goal here is not to learn these new concepts, but rather learn how to prove some basic properties involving these concepts. So, an integer n, as you certainly know, is even if and only if there exists an integer k such that n is equal to 2k. And it is odd if there exists a k such that n equals 2k plus 1. An integer is prime if and only if it is greater than 1, and if for all positive integers a and b, if n equals a times b, then n equals a or n equals b. Now this is probably a little different from how you learned about prime numbers in grade school. There it's often defined where a number is prime, a number greater than 1 is prime, if its only divisors, only positive divisors, are 1 and n. And let me just take a moment to convince you why this statement is equivalent. I'm not going to prove it, but hopefully give you enough evidence to convince you of it if you don't see it already. So I'll just do it by example. So if n is a prime number such as 5, then the only way to factor 5 is 1 times 5 or 5 times 1. There's no other ways. And so that means if you can write 5 as a product of two things, then one of them has to be 1 and one of them has to be 5. And that's exactly what this is saying right here. Conversely, if n is not prime, let's suppose n equals 6, then 6 equals 2 times 3 or 3 times 2, then there is a way to write a composite number as a product of two integers that are strictly between 1 and 6. So that brings us to the definition of composite. An integer is composite if it is greater than 1, and if there exists some integers, a and b, strictly between 1 and n, such that n equals a times b. Before we actually do any proofs in this lecture, I'm going to give you 4 examples of statements, and let's just think about what would be needed to establish them. The first one is an example of proving an existential statement. So suppose we wanted to show that there exists an even integer that can be written as a sum of two prime numbers in two different ways. To establish this, all we have to do is find such an integer. That's it. Then we're done. Next is an example of disproving an existential statement. For example, suppose that we wanted to show that there does not exist integers a, b, and c, and an exponent n greater than 2, such that a to the n plus b to the n equals c to the n. Now, you might recognize this. This is Fermat's last theorem, which was proven after hundreds of years, finally in 1993, by Andrew Wiles at Princeton, who worked on it alone for 7 years, and his proof was several hundred pages. Now, coming up with a simple example is not going to do the trick. You have to show that this statement, this conclusion, is false for all integers a, b, and c, and n greater than 2. So disproving an existential statement is equivalent to proving a universal statement. And that's the next example, proving a universal statement. For example, what if I asked you to show that 2 to the 2 to the n plus 1 is prime for all integers, positive integers, n? That's something that you can't just exhaustively check cases, because there's infinitely many of them. So you have to come up with a reason why it should hold for all n. Finally, our last thought experiment is how to disprove a universal statement. For example, consider the same statement that I just gave you. 2 to the n plus 1 is prime for all n. Suppose I told you that was false. How would you disprove it? Well, all you have to do then is find a single instance of n for which 2 to the n plus 1 is composite. and then you're done. So is this true or false? Well, this is something that we will come back to in the next lecture, so stay tuned. On this lecture, we'll focus mostly on parity, that is, even and odd integers, and our proofs will mostly be on existential statements. Though, as I said, disproving an existential statement can be recasted as proving a universal statement. An existential statement is often of the form, there exists some x in U such that the conclusion Q of x is true. This holds if Q of x is true for at least one element in the universe. There are several ways to prove such a statement. First of all, constructively, you can find or construct such an x. Non-constructively, sometimes we can show that such an x must exist either by an axiom, theorem, or other means, even though we can't tell you exactly what that x is, other than there just has to be one. And finally, indirectly, we can do it by contrapositive or contradiction. So I will give you examples of all of these. Let's start simple. Before I do, let me mention something about the use of the word proposition. If I haven't already, I don't remember if I have. We learned in propositional calculus that a proposition is a logical statement that is either true or false, possibly depending on a value that you plug into it. However, in mathematics, outside of logic, the term proposition typically means a statement that is true. So think of it like a minor theorem. We usually use theorem when it's a big central result. Okay, so here's a quick proposition that there exists an integer that can be written as a sum of two prime numbers in two different ways. To prove this, we will find such an integer. And it's not hard to come up with one. You don't need to go that big. Note that 10 can be written as 5 plus 5 or 3 plus 7. Now we're done. So I'm using the term find because I didn't come up with a formula or tell you how to find one. I explicitly gave you an example. Our next example is a little bit harder, but not too much. This says, if n and m are odd integers, then n plus m is even. In other words, n plus m equals 2k for some integer k. So this is can be phrased as an existential statement because here I am saying there exists an integer k such that n plus m equals 2k. However, notice that I can also cast this as a universal statement. I could say for all odd integers n and m, I could say that n plus m is even. So these statements are not necessarily only considered existential or universal. There is a little bit of a gray area. They're not just black or white. But I'm going to choose to think of this as an existential statement and prove it that way. And specifically, I mean that we are going to construct such a k that works. So up here we found such an example. Now I'm going to give you a formula, an explicit formula for such a k. And let's do that now. Again, constructing a way to write n plus m as 2k is different than finding such an answer that works for all cases. So first I will start by writing n as 2a plus 1 and m as 2b plus 1 for integers a and b. And now think about what I'm going to do next. I'm going to add these together, and I want to show that that sum is twice of some integer. So n plus m, which of course is 2a plus 1 plus 2b plus 1, is equal to 2 times a plus b plus 2, which is 2 times a plus b plus 1. So there's my integer k, and this establishes that n plus m is even. So it's a little bit more work. Again, above I just found such an example that worked, and here I had to construct such an example in terms of an arbitrary choice of n and m. The previous examples were constructive proofs of existential statements. Now, on this slide, I will do a non-constructive proof and an indirect proof. First, consider the following statement. There exist irrational numbers x and y such that x to the y is rational. This seems first a little bit hard to believe because how can you take a irrational number like pi or root 2 and raise it to some other irrational number and magically things cancel out and you get a fraction? I should mention what a rational number is. I think you probably know, but irrational number is of the form a over b, where a and b are integers. Many books will specify that b has to be non-zero. I don't think this is necessary because if b is, well, it's obviously a necessary requirement, but you don't have to say it because if b is 0, then a over b is meaningless. So we will actually formally define rational and irrational numbers in a couple of slides, and a couple of lectures, and we will study them in more detail and prove things like the square root of 2 is irrational. But for now, we will assume the definition because, again, we've all seen it before. And we will also assume the fact that the square root of 2 is indeed irrational. So if we want to show that x over y is rational for some irrational numbers, then if it's a constructive proof, we would have to show what the a and the b are. So we'd probably have to cook up a particular x and a particular y for which this is a fraction. And I don't know how to do that. That seems hard. But what's really neat about this non-constructive proof is I will show that there has to be such a pair, but I won't necessarily tell you what it is, because I don't know how to tell you what it is. Okay, so how does this work? First, if root 2 to the root 2 is rational, and we're done. In this case, x and y are just root 2. Now, I don't know if this is rational. I don't know how to check that. It certainly doesn't seem like it should be rational. And I would bet money that it's not. But again, I wouldn't bet a ton of money. So if it's rational, we're done. Let's assume that it's not rational and see how to deal with that case. If it's irrational, then let's let x be root 2 to the root 2 and let y be root 2. Then x to the y is root 2 to the root 2 to the root 2. And by rules of exponents, we multiply these exponents. And this is just root 2 raised to the power of, this is 2, in other words, root 2 squared, which is 2. So in conclusion, I don't know which of these examples is the one that makes this existential statement true. I don't know if it is x and y are both root 2, or if it is x being root 2 to the root 2 and y to the root 2, but I know that one of these has to be the example that we seek. So again, we proved existence without actually constructing which one it is. And again, for the record, I would bet money that this is the actual example, but I can't prove it. Finally, we come to our indirect proof. I claim that if 5n plus 2 is odd, then n is odd. In other words, this premise implies this conclusion. And it turns out that actually this is an if and only if, because it's pretty simple to show that if n is odd, 5n plus 2 is odd as well. Let me just take a brief detour to do that. So if n is odd, this is proving the backwards direction. If n is odd, then I'm going to let n be equal to 2k plus 1. Then 5n plus 2 is 5 times 2k plus 1 plus 2, which, what is this? This is 10k plus 7, which is 2 times 5k plus 3 plus 1. So that shows that 5n plus 2 is odd because 5n plus 2 is 2 times some integer plus 1. Okay, so that's a direct proof is easy. But the other direction, the one that I've stated here, if 5n plus 2 is odd, why is n odd? Now you can try a similar thing. You can say, so let's try this. Let's suppose that 5n plus 2 is odd, and let's say that 5n plus 2 equals 2 times k plus 1 for some integer k. Now we want to show that n is odd. So how are we going to do that directly? So we can try to solve for n, and we get that n equals 1/5 times 2k minus 1, and that's not even clear that that is an integer. So we don't really have too much to work with. It seems like it should work, but we kind of get stuck. So I encourage you to pause the video if you need to, but convince yourself why this has to be true. Make a convincing argument in your head. If 5n plus 2 is odd, then n has to be odd. You got it? I bet that if you did this successfully, you probably convince yourself that, let's see, if this implies that, well, if n is even, then 5n plus 2 is definitely even. And so that's why it's true. In other words, you convince yourself of the contrapositive. Well, if not, then stick around and I'll do it right now for you. So recall that the contrapositive just says that if, let's call this Q of n is false, then P of n is false. So if n is even, then 5n plus 2 is even. So let's suppose that n is even. In other words, n is 2 times k. And I don't always have to write that k is an integer because it's usually understood from the context, especially if we use n and k. Then 5n plus 2, I claim this is even, that's what we're trying to do, is 5 times 2k plus 2. Now remember what we're trying to do? We are trying to write this as 2 times some integer. So do you see how to do that? We will write it as 2 times 5k plus 1, which means that it is an even number by definition. Okay, so this is an example of a statement that was very difficult, if not infeasible, to prove directly, but an indirect proof, namely the contrapositive, fell out right away. Okay, so let me mention the same thing that I did a few slides ago. That this is one example of something that I'm saying is an existential statement, but you could also cast it as a universal statement as well. So for example, as an existential, or with an existential quantifier, I could say if 5n plus 2 is odd, then there exists an integer k such that n equals 2k plus 1. So there's my existential quantifier. Or I could cast it with a universal quantifier. So I could say for all integers n, if 5n plus 2 is odd, then n is odd. The purpose of this lecture is to get you used to different types of proofs. All of them loosely involve an existential quantifier. So I'm going to do one just for more practice, something that's very simple. An integer n is even if and only if n plus 1 is odd. So the point of this is not to enlighten you with a brand new result, but rather to get you to practice these proof techniques and using the definition. Now here, this is an if and only if proof. So one thing that you probably might want to try first is to prove the forward direction and then the backwards direction. So let's just do that. And then when we're done, we'll see if there's a way that we can simplify the proof. So the proof, we'll start with the forward direction. So suppose n is even, and in this case we can say that n equals 2k for some integer k. Now we don't need to write for some integer k because I think it is implied by the context, but it's sort of like writing code or writing comments in your code. And some people comment more extensively than others. It depends on how much you want to explain, and there's always a trade-off of brevity versus just having more information in there. Okay, so suppose n is even. We want to show that n plus 1 is odd. So let's just follow our nose. Then n plus 1 equals 2k plus 1, which is odd. You could just say which is odd, or you can say which is odd by definition. And this is just to remind the reader why, because if you just say this is odd, you might leave the reader hanging. So that confirms that direction, and now let's do the converse. So for the converse, we are going to assume that n plus 1 is odd. So suppose n plus 1 is odd. In this case, we can say that n plus 1 equals 2k plus 1. And I'm not going to repeat that k is an integer. I think that is clear. Now, some people will not like to reuse the letter k, so they might say n plus 1 equals 2l plus 1, and that's fine, but I think it's fine to do that here. So n plus 1 equals 2k plus 1, and our goal is to show that n is even. So then n, if we subtract 1 from both sides, we get that n equals 2k, so n is even. And that proves that direction, and that completes the proof. Now, you may be looking at this and say, well, that was pretty trivial. Both of these directions were almost the same. And you would be right. This is something that we can shorten. So what I will do is I will show you how to write a shorter proof of this. And it's basically because all of these steps, suppose n is even, then this, then that, then this, these are if and only if statements. So I'm going to write down some notes and then we'll discuss how to write it up nicely. So here's my proof. So n is even if and only if n equals 2k for some integer k. And this is true if and only if n plus 1 equals 2k plus 1. You can't stop me from adding 1 to both sides of the equation, and I'll say for some k. And this is true if and only if n plus 1 is odd. And this is by definition. And so that's it. We started with our assumption, and we showed that this, through a sequence of equivalences, that is equivalent to our conclusion. Okay, so I think this is probably a cleaner way to write the proof. And sometimes, depending on the context, like if you were to write this up in a textbook, you might want to start with an introductory sentence and then conclude with a sentence. But that's more just a writing style. I think this is perfectly fine in this class. Okay, so all you need now is an end of proof box. Now most statements like this, most if and only if statements, are not quite as simple as this. Often, as we've seen, there are very different methods for showing that A implies B compared to B implies A. But sometimes you can do it in one fell swoop like this. At last, we come to the last slide. Disproving existential statements. So to disprove a statement like the following, there exists an X in the universe such that Q of X is true. So we have to take the negation of that. We have to show that for all X in U, Q of X is false. Remember that trick? Negating an existential statement turns it into a universal statement, but the negation attaches onto this thing. So to do this, we have to prove a universal statement. And this will be the focus of the next lecture. However, as I've mentioned, we've actually done a few of these already. For example, recall our earlier result, slightly rephrased, that for all odd integers n and m, the sum is even. So remember, the sum being even, we could write as there exists an integer k such that n plus m equals 2k. Okay, so more of these universal statements in the next lecture. Stay with us.